Hi and welcome to the first of our higher level bonding videos, and we'll be looking at molecular geometry. This is essentially molecular shape that we've seen in SL, and we'll be adding on to that with some new shapes. So, key things here is we'll be reviewing molecular shape and how it influences physical properties of a substance. We'll have a quick look at the SL shapes and bond angles that we've seen previously, then move on to new structures involving 4, 5, and 6 charge centers, which will require us to look at a couple of molecules that can expand their octet, such as molecules involving sulfur and phosphorus, such as PCl5, sulfuric acid, and things like that. Okay, so just a quick review on how the shape of a molecule influences properties. We know that how the shape is formed determines how a molecule interacts with the molecules around it. This gives us terms like packing, so whether or not molecules are able to pack closely together because their intermolecular forces are distance dependent, and also steric hindrance, which we saw in organic when we talked about stabilization of the carbocations. The shape of the molecule also influences its polarity, as we saw with something like water. That bent shape means that the dipoles are not distributed symmetrically around the molecules, so we start to see polar molecules forming, which changes our intermolecular forces. In terms of physical properties, we've also seen that a straight chain hydrocarbon such as pentane is able to stack more closely together, giving it a higher boiling point, 36.1 degrees in this case, compared to the branched isomer of dimethylpropane, which has the boiling point of 9.5 because of that branch structure, reducing the ability for the molecules to stack, therefore reducing the influence of the overall dispersion forces. For SL, we looked at a number of shapes where we looked at the number of charge centers around a molecule. We looked at single, double, or triple bond being a single negative charge center, counting those and looking at the number of lone pairs in order to determine the overall shape. These are ones that we've reviewed briefly recently, so I'm not going to go through them in detail. But just remember that with the bond angles, the greater the number of lone pairs on that central atom, the more it's going to influence your bond angle. So if we have a V-shaped molecule like SO2, where there is one lone pair, the bond angle will be just under 120 because of the influence of the lone pair at 117 degrees. Whereas if we have two lone pairs on that V-shaped molecule, then it's going to be at about 104.5. So looking at these, this is just a way to sort of talk about the number of charge centers and lone pairs around a molecule. These diagrams use an AXE notation, where we have A being the central atom, X being the groups that are attached to it, and the E being the electron pairs. So looking at these, our original linear shape is AX2 with a bond angle of 180 degrees. Bent or V-shaped molecules are AX2E, remembering that more bent shape is AX2E2. Okay, then we can have AX3, which is our trigonal planar, remembering that a lot of our trigonal planar molecules are shown with boron, but we can also see that with organic compounds where we have a C double bond O going out to two other groups as well. And then we have our trigonal pyramidal with ammonia, or molecules where we have 3 bonding pairs and the 1 or 2 bonding pairs on top. Sorry, 1 bonding pair in this case. And the bond angle there will be less than 120 degrees as well. With expanded octets, what we see is that there are some atoms which are able to form bonds with more electrons in their valence shell than the 8. We've seen some of these compounds before, such as PCl5 and even our sulfate anion or sulfuric acid. What we see here is that the period 3 elements are often the ones that can do this, and they form covalently bonded compounds with 5 or 6 electron domains. We look at the phosphorus compound here, PCl5. Whoops, not 2, 5. Okay, we can see that our bond angles around here, we have a central plane and then a bond above and below. This gives us 5 bonds around the central atom, which is 10 electrons. And in sulfuric acid, we can see here that we have 2 double bonds to oxygen and then 2 single bonds. So this is going to give us 2, 4, 6, 8. Okay, then 10 and 12 electrons in the valence shell. So it's important to remember that these occur because these are the types of molecules that we see with the new shapes that we'll be looking at. So we talked about 1, 2, and 3 electron domains. So now we're going to talk about 4, 5, and 6. The 4 that we've seen before is tetrahedral, and this is our SL4 electron domain. In HL, we see a number of others. We have square planar, trigonal bipyramidal, and octahedron. So square planar is an AX4 2E configuration. Trigonal bipyramidal is an AX5 configuration. And then we have octahedral with an AX6 configuration. Each one of these we will look at in detail. So when we're talking about 5 charge centers with no non-bonding pairs, the shape that we get is a trigonal bipyramidal. It's 5 atoms, each bonded to the central atom as we see here. Okay, and if we think about it, it can be thought of 2 trigonal pyramids fused together at their bases. So we have the one here going down to each 3, and then that one fused, another one fused to the bottom of it. This means that what we have is a trigonal planar arrangement through the central plane where the bonds are 120 degrees between each atom, and then the bonds that form above and below the plane, which will have a 90-degree bond angle to the plane. This is the shape that we see with PCl5. We can also see molecules with 5 electron domains where we have bonding pairs and non-bonding pairs. In this case, we can have 3 bonding pairs and 2 non-bonding pairs, which gives us a T-shaped molecule that we see on the left over here. These are fairly unusual compounds that form under special conditions. So we can see here we have an F3Cl, which has 2 lone pairs on the central chlorine and 3 fluorines. This is a T-shaped molecule where we have 90 degrees between each bond. The other one that we can see is 4 bonding pairs and 1 non-bonding pair. This is referred to as a seesaw configuration, and we have 90 degrees between the bromines that are linear to each other and the bent configuration ones. So we see 90 degrees here, and then 120 degrees between the base ones around that form that V shape. Okay, we can also see 2 bonding pairs and 3 non-bonding pairs, which we see with a molecule known as xenon difluoride. This will have a linear configuration where we have the non-bonding pairs form around that central atom, pushing the 2 fluorines away at 180 degrees. So these are the ones that we've talked about so far. We have trigonal bipyramidal, seesaw, T-shaped, and then we have linear where we have 5 electron domains, which is our xenon F2. There are examples of each of these that you should be familiar with, and also the number of bonds and non-bonding pairs involved. If we have a pure 5 bonding pairs to the central atom, it'll be a trigonal bipyramidal. 4 and 1 non-bonding pair, seesaw. 3 and 2 non-bonding pairs, T-shaped. And then we have 2 bonding pairs and 3 non-bonding pairs, we see a linear shape. Moving on to molecules with 6 charge centers and no non-bonding pairs, we get our octahedron. As trigonal bipyramidal was 2 triangle-based pyramids fused together, An octahedral complex is two square-based pyramids sat together at their bases. This is 4 atoms in a plane to form a square planar situation around the central atom. Then we have 2 atoms above and below. Okay, so this means that we have 90 degrees to the plane, and then we have 90 degrees within that square pyramid in the center as well. Okay, so because we have 4 here and they are flat in a plane, they will be 90 degrees like a square planar complex. And then we have the bond that rises above the plane and below the plane, which will also be 90 degrees. An example of this is PF6 and also SF6. You'll notice that in some of these interesting ones, fluorine is certainly a large contributor to these molecules. So if we look at molecules that have 6 charge centers with non-bonding pairs, we can have 4 bonding pairs and 2 non-bonding pairs around the central atom. This gives us a square planar complex where each of the bonding pairs is in a plane at 90 degrees to each other around the central atom, with the non-bonding pairs now taking positions above and below the plane. We refer to these as axial positions when they are above and below. And then the bonding pairs are what we call equatorial, okay, around the central atom at that midpoint. Xenon tetrafluoride is an exception to many rules, one of them being that it is a noble gas that has formed covalent bonds. Okay, so it also has interesting bonding in the formation of this square planar shape. One of the other molecules that we see here is a square pyramidal. So this is essentially a square-based pyramid where we can see that we have 5 non-bonding pairs and then we have 1 non-bonding pair that comes out from the base of the pyramid like thrust from a rocket. Okay, so the bond angle between all fluorine atoms and the xenon in this is 90 degrees, as we saw with the octahedral complex, but this time we only have that 1 pyramid, not the 2 fused together. So this is a summary of each of those shapes, which have our 6 electron domains. So we have 6 bonding domains and we have octahedral, 5 with 1 lone pair, we have square pyramidal, 4 with 2 lone pairs, we have square planar. So that's it for all the new shapes. If you need to review SL, you can go back to the old video on SL shapes. Next up, we'll have another quick review of sigma and pi bonds before we move into talking about hybridized orbitals.